So I mean, I know Tim, he sent me the results, but other folks, did you have a chance to give that a try? The matrix multiplication. It's not an assignment, but it's a good way to get familiarized with using NumPy and using Colab or Jupyter notebooks. Did anyone had any trouble trying to run that, task? No problem. And like it's not a really an assignment, so you don't have to really do it, but it's just to like have to get you familiarized. I also have added one more task here for this week, and again, this is still not an assignment, so if you don't submit it, that's fine. But just doing this task will allow you to appreciate some of the things we'll study today. And next week I will actually add the first assignment, which will be graded. Okay, so let's begin. Now, this week is where we'll actually get into the building blocks of deep learning and neural networks. Right? When people say deep learning, it's and almost always like deep neural networks. And you in order to get to deep neural networks, you need to first study neural networks on its own, because that deep component comes later on. And the most simplest version of a neural network is called as a perceptron, and you will see it goes back long back, even before people had the idea of AI. And then and then also we'll study some of the building blocks, and these are the things that will be used to compile this really big deep neural networks. Now, the idea for this, I think I alluded it slightly last time, is that the reason the word neural is there is because it's loosely inspired from human neurons. And a typical neuron cell looks like this. Right? It has a nucleus. This is the main cell body. And each cell has a lot of these connections. And then of course there is this big piece called as myelin sheath, or sorry, axon. And then again it goes and connects to other neurons. Here, I'm just showing you a single neuron, but in reality, it's a lot. Each neuron is connected to several neurons. I think the number of neurons are in the order of hundreds of billions, and the number of total connections are in the order of trillions in a human brain. So you can imagine how many neurons you're talking about. But until a few years ago, all the deep neural networks were much smaller compared to human brain. But now we're slowly starting to get, with some of the big models that Google and Facebook they're training, we're kind of getting towards the area where like 100 billion neurons are being used in deep net. So they are kind of getting to that territory. But for this assignment and for all practical purposes, I would say a couple of million neurons is where we will be at, and those are sufficient to actually do some of the complicated tasks. And again, you don't have to understand the parts of the neuron. This image is just to give an idea that why this is a deep neural network. The neural comes from the neurons. Now here you can see this was published like 1943. This is where they had this idea of using neurons as a way to generate some kind of information. And here again, the idea is you have some number of inputs, and there are these weights. And again, we'll come to what these inputs are, what these weights are. But then it is loosely inspired from this, because in human neuron also you have all these connections. They are either input or they are output. So in this particular case, it could be an input here, it could be output here, and some kind of a computation happens within the cell body, and then that output is passed. Similarly, here we have a bunch of inputs, some kind of computation that happens. In this particular case, it was a simple weighted sum, and then there's a threshold. And if this weighted sum is higher than the threshold, we call it positive signal. And if it is lower, it's there's no signal. And that is how neurons also work. They either fire or they don't fire. There's no idea of partially firing. And that is where this idea comes, that all these inputs, now if you didn't have these weights, then this will be like a simply adding all the inputs, and if all the inputs are above threshold. But some of the inputs are more important than the others. And this importance of input is characterized by having weights. So for example, if weight for x1 were 100x larger than all the other ones, then you can clearly see how x1 will dominate, right? And of course, now what the real weights are, in the human brain, we don't know. It's impossible to find out. But as far as neural networks goes, these weights, these are just your variables, and we will figure out how to find these values. Either these values can be hard coded, or these values can be optimized for a certain task. And you'll see over the course of this whole course that there are many different ways for uh, finding these weights, these values. And these values represent how important these inputs will be in order to do this task. Now again, let's make sure that we all have this terminology that we all agree upon, right? So whenever I say input, like there will be a bunch of input links, right? So here in this case, x1, x2 up to xm would be input. And then in the middle you have some idea called as activation function. And you will see why it's called activation, because either it activates or it doesn't activate. And then this will lead to output. And most of the time you will see that there is a single output, but that doesn't mean that the output has to be a single. There could be multiple outputs, and each of the output could then connect to other parts of the system also. So this is overall like a general idea of what a perceptron is. Because when I say perceptron, it doesn't always have to look like the original proposed perceptron. It could look like anything which meets this category. So when somebody were to ask you, design me a perceptron, however you design it, it'll basically have these blocks. Now, typically, if you just Google perceptron or neural networks, this is the kind of the diagram you will get. And here, each line. Now, what is the difference between this and this? Here, you will see that each of the input is connected to some node, right? And then this node is again connected to some other node which is called as output. So in this case, you have this something in the middle, like these middle ones are also like your neurons. And this whole package is called as like a perceptron network, right? Because this is actually a network of all these neurons. Each individual circle is a neuron. It has a bunch of inputs and it has a bunch of outputs. Now, what does each arrow represent here? Each arrow is a single number, right? It could be a floating point number, it could be a complex number, whatever it is. These are all number, and these number represent how these inputs will be weighted. And by just by playing with the values of these weights, we'll be able to determine the output. And we will try to work out an example. But as far as the terminology goes, this middle neuron, this is called as hidden neurons. And typically you'll see this is it's almost as if that this circle, this circle, this circle, they're all in one layer, and therefore this is what is called as a hidden layer. And in deep learning, you'll often see the word layer being used a lot. And if you have played around with Keras, or if you read the book, if you read the first chapter, you will see that the word layer is always used. The layer is just is all the set of inputs, so all these neurons that share the same input, right? Because you'll see here 1, 2, 3, 4, all of them share the same inputs. Now, in 2 weeks, we will learn that it doesn't always have to be represented like this, but this is the most basic form of a perceptron. And again, if you guys have any question in the middle, feel free to put in the chat or just, ask directly. I don't mind being interrupted. Now, ultimately, the power of this neural network comes because it is able to do all the kind of the computation that you would imagine a computer to be able to do, right? Because when you think of digital computer or any kind of electronic device, we think of these logical gates. Let me see, are only the hidden nodes true neurons? That's a good question. Let me go back. I don't think there's any answer to this, right? Because people think all of this as neural network. are only the hidden ones true neuron? If you ask me personally, I'll say yes, but most of the time the definition is vague. There's no really true neurons to speak, because people don't talk in terms of neurons. People only talk in terms of layers. And in this case, you have one layer, or one hidden layer. You could also have two sets of hidden layer. You could have three hidden layers, and then when you have a lot of hidden layers, that is where it becomes deep, and then you get the idea of deep neural network. So people don't talk in terms of neurons, but if you ask me, yes, I would say only the hidden neurons are true neurons, because they they take input and they give the output, whereas in the case of input, there is no input coming to itself, right? So in that way, yes, but to be honest, the answer would be it depends. Okay, now coming back to this, like I said, these logical gates are the basic, computing blocks, right? You need to be able to do these logical gates computations in order to represent any digital information. And we know there are these universal gates and other type of gates, and when you put a lot of these gates, you basically make a computer system. So let's see if we can, and again, if you guys have pen and paper, please try to work it out. I will go as slow as I can, but it'll be nice if you can work it out yourself. So again, forget about the figure on the right. The table on the left is your logical AND gate, and I hope everyone here knows what's an AND gate, right? Where when you have when both the inputs is true, only then the output is true. Otherwise, in every other case, the output is false. And again, here I'm just making it simple. I'm just considering two inputs, but a logical gate could have n number of inputs. But the idea is that only when all the gates are on, the whole thing is on. Otherwise, the whole thing is off, right? So we want to be able to represent this behavior. So if x1 and x2 are my inputs, the question that is being asked to you is, what should the values of these weights W1 and W2 should be, such that if x1 x2 is on, I want the final output to be on, and if x1 or x2 either of them or both of them are 0, I want the final output to be 0, right? So for simplicity's sake, let's assume again, forget about this circle which is t1.5. Let's simply say that the computation that happens in the neuron here is simply adding both of this, right? So if you simply add both of this, you can see here when both of them are on, it becomes 2, and we can just say 2 is same as 1, because in digital computing there's only 2 numbers, right? It's binary, so 1 or 0. So 2 is also positive, so we'll call it on. So when both of it is on, it's on, that's correct. Now, if x1 is on, that is 1, and x2 is off, that is 0, then this will be 0 multiplied by 1, that is 0, 1 multiplied by 1, 1, and when you add 1 and 0, it becomes 1. So you would get a signal if either of them is on. So you can see how this breaks the pattern that we want this perceptron to achieve. We want where if x1 is on and x2 is off, we want the whole thing to be off. So in this case, what we can do is we can assume that there is a threshold, right? And here T represents a threshold value. So here the signal could be something like, one second. So let's say it could be something like this. Let's call it here S. So S is the intermediate output here, where S is equals to x1 multiplied by W1 plus x2 multiplied by W2. And the final output is basically equals to S greater than T, right? So this is our logic. That is only when S is greater than T, then if this is true, then the output will be equal to 1. Here, let me write like this. So say this is how I'm going to do my computation. Now in this case, if this both is 1, so you will get 1 multiplied by 1, this is 1, this is 1, 1 plus 1 is 2, 2 is greater than 1.5, therefore output is 1. If this is 1 and this is 0, I would get 1, and 1 is not greater than 1.5, so it would be 0, right? And then you can see how it's the same thing for the other way around. And if both of them are 0, 0 is less than 1.5, and therefore output is 0. And that is why this gate is being represented if you had this computation. Any questions from anyone? Is it clear how this logical AND gate has been represented here? Okay, I hope there's a question here. Okay, perfect. Thanks, Tim. Okay, now let's try to represent OR gate, right? In the case of OR gate, it's almost complementary to AND, right? That is only when both the signals are 0, you want the output to be 0. That is, when I say 0, think of it as no signal or not activated or off, whatever it is. But in any other case, you want it to be 1. Now, again, this is where if you have pen and paper, I'll give you 2 minutes. Don't look at these numbers. Try to work it out yourself. See if, if the threshold were 0.5, and if now, what kind of function should there be here? So what does S look like, right? Because in the previous case, I told you S was simply weighted sum of inputs. Now, in this case, what kind of functions should S be, such that I'm able to represent this? And you are feel free to change what the threshold value should be. And again, if you're not sure, try to use the same function as here. But if you want to be creative, try to find another function which, again, you can play with x1, w1, x2, w2, and then you can represent the S with that function. And then you can use the threshold or not use the threshold and see if you can work it out to get to this table. That's a very good question, Kyle. Yes, if you want, you can use max. So the only requirement here is, S is a function of x1, x2, w1, w2. And again, you don't even have to use all of this. Just because it is function of all of these things doesn't mean you have to use all of them. But and if you want to use max, go for it. You can use max also. But towards the end of the class, I will show you that max is definitely interesting for some. It has some interesting properties. Okay, I will give you a minute if you are trying to work it out. If not, feel free to work it out after the lecture. And again, if you are really inclined, try to see what would happen. So here the value threshold T 0.5 is really when you have 2 inputs, right? If I had 3 inputs, then this threshold of 0.5 would not work, right? The threshold will have to be something else. So if I tell you that there are 52 inputs, what should the value of threshold be if the function is S? That is a simply linear weighted sum. What should be the value of T? And there, so now you want to be able to write T in terms of N being number of inputs. And if you think about it just for a minute, you should be able to work it out. There's a very simple formula that will come out where the threshold is automatically determined as long as the function is simple like this. If the function is more complicated, then probably threshold will the computation for threshold will be even harder. Okay, I will go ahead, but if you're working out, let me know in chat. If not, let's go to the other gates. NOT gate is very simple, right? When NOT gate is one of those things that only takes a single input, right? So, and again, when I say perceptron has inputs, it could still be only one input, right? It doesn't always have to have multiple inputs. So in this case, whatever is a signal, we want to reverse it. And now here, again, either you can take a leap of faith here, that if I tell you that if my weight is -1 and threshold is -0.5, you can use the same linear weighted sum as a activation function. And by the way, here when I said S, this function, this is what is called as activation function, right? If you remember from this diagram. This is what we're trying to figure out. But this doesn't mean this is the only solution. This is one solution to represent this logic, but there could be many other solutions. You could have different weights, you could have different threshold, and also you could have a different function. But as long as your function is simple like this, you can do with this. And please feel free to work it out to make sure it works like this. Now this is where I would definitely want to pause, and I want you guys to sit down. I will give you 5 minutes, and you might like, this is important. Why? Because when you're trying to debug your neural network later on, this is where your understanding of how these things are composed will become key in your ability to debug the stuff. So here I want to represent exclusive OR gate. And again, if you guys don't know exclusive OR, it is when if both the inputs are same, output is 0. Doesn't matter if it is both on, output is off. If it is both off, output is off. It is on only when one of the input is different than the other. So in this case, 0 and 1, it should be on. 1 and 0, it should be on this. So it's 6:20. I will give you 5 minutes. Please try it out. Whoever has the answer first, I can give you 1 bonus point in your assignment if you come up with the answer. For timing, I will mute my computer, but feel free to ask clarifications in the chat, and I will be watching the chat. So you have 5 minutes max, and try to work it out. If not, you can ask questions regarding some of the previous slides. And again, you are not limited to the linear weighted sum as an activation function, although that would be nice and easy to do. The function like this, but if you want, you can try some other functions also. That's a good question regarding threshold, Kyle. It'll be nice if it is strictly greater than, because later on you will see that like that has a significant impact. But if you're struggling to do with simple threshold, I will allow you to play with another kind of threshold functions. Let's see. Jamie has an answer. Tim has an answer. W1 and 2 x squared by 2. And when you write down the answer, I hope you are trying to think of it as a generic form, where instead of 2 inputs, if I had like 4 inputs or like 3 inputs, although I don't know how exclusive OR gate would work with 4 inputs. Okay, maybe I will stick with 2 inputs here. Okay, let's see if Jamie's answer works out. -1, -1. T is -0.5. So if I have -1 plus minus 0.5. Jamie, I don't think your answer works out, right? Because if it is -1, in the case of the second row, it would be -1. And is -1 greater than -0.5? No. Yeah. So yeah, so Jim's answer doesn't work out. Let's see Tim's answer. Tim's W1 and 2. X squared by, I'm hoping there's X squared.
Yeah, so it's square the input and then divide the answer by 2 and then add them together. Sorry, they're supposed to be summed, but yeah.
I see. Okay, so sum of the squares of the input, right? Okay, let's
So
see.
sum of the squares of the input divided by 2. So take the input, square it, divide by 2, and then sum them.
Okay, so let's try to do this 1, 1, right? So if I take, so this square of 1 is 1, square of 1 is 1, so 1 plus 1 is 2, 2 by 2 is 1. So you can see in your case, for the final row, it works for the first 3, but for the final row, the output is still 1, right? Oh, I see. You have
No.
t has to be less than 1. Is it correct?
Less than, not less than or equal to, but
Okay.
less than. It has to be bound between 0 and 1, but it can't be equal to 0 or 1.
Yeah, so that's the trick. So Kyle says 1, 1, and threshold is 1. So if it is 1, 1, 1, so, oh, I see. In your case, you're saying, so Kyle, in your case, is it greater than threshold, or are you also using some kind of a bounded threshold?
No, instead of having a threshold of greater than, I know you said that would be preferable, but I said that the threshold would be, it has to exactly equal 1.
Okay, I see. Yeah, so this, okay, so it's interesting because, you know, you guys have all very quickly kind of conversed that it seems it's impossible to do if your threshold is strictly greater kind of thing, right? Now, as far as, you know, like perceptron goes, whether it is artificial, you know, like this kind of a neural network setup, or whether it is human brain, typically it is, you know, like the threshold is unbounded, like a one directional. Why? Because the way in brain it works is, if enough neuromodulators, so these are like your chemicals in the brain, so if there's enough of the molecules, because there's like fixed number of binders in your neuron cells, right? So if there is more neuromodulators than the binders, then it is positive. But if it is less, that is, if the number of neuromodulator molecules are less than the places to bind, then, you know, it is less than the threshold. So both naturally as well as artificially in this thing, it is so much easier to actually implement with a strict threshold. So as far as, you know, using strict threshold goes, it is technically impossible to do. I will slightly give you an idea later on, and you will see why. You know, there's this big thing called as XOR problem. So for the first time when this was proposed in around, like, I think 70s or 80s, people were like, oh, if neural networks cannot solve a trivial problem like XOR, clearly they are of no no real value. But you will see later on that restriction only applies if you have this one hidden layer. And when you add a second hidden layer, that is equivalent of playing with your threshold. That is, instead of this t just being a single value, what if t were also a complicated function? Because every function is just like, you know, your one set of hidden layer. So if you treat this as another hidden layer, that is, it also has an activation function, then it is possible to do. So the easiest way to solve XOR problem is to basically assume you have two sets of function. That is, second set of function takes input from the output of the first set of functions. So you are feeding this output to this input, and now this is also a more complicated function. That is, it is not possible to do by simply using a threshold. Now you will say, why is it considered, you know, two layers of neural network? Why is it not one layer? Because in practice, this threshold is implemented implemented like this. Here, let me write it down. even though I did show you this, threshold, threshold as, the way it's represented here, it seems like it's a separate layer, but in practice, the threshold is almost represented like this, minus threshold, right? And typically, so this threshold is, so again, instead of using T, this is represented W0. And this W0 is very meaningful. So now, this node is not there, it's just part of this function S. And now, this still, so now if this value is positive, then, it is on. If this value is negative, then it is off, right? So you can see we are still within this one layer where, basically this X0 doesn't have any input. So oftentimes you will see, if you read different textbooks, you'll find there is a separate connection here, which doesn't go through any input. And there will be a word called as bias. And bias is basically a threshold or W0 or whatever it is. And this is still another one of these weights that, has to be figured out. But the purpose of bias is to, is to act like a threshold. So in that case, this is still represented as a single layer. But like you guys figured out, if this bias were to be after this S is computed, that is not as a part of S, but if this bias could be outside, that is, it is two layer of neurons, one feeding to the other, then you can solve XOR problem. But it is not possible to solve XOR problem if you had to do your computation as a single layer like this. Is that explanation clear or do you guys still have doubt on why it is done this way? Okay, so yeah, of course, don't go home trying to figure this out, because if you just try to do it as a single value, it would not work out. It's not possible. Okay, now let's go back to more practical problems. So again, let's remind ourselves all these terminologies, and let's make sure we agree on the symbols. And here you can see here now, this is the same thing as the bias which I said, right? Because now you can assume that that input is always on. So basically this W0 bias, this can be like a negative value, and everything else is your input. And now there's activation in the middle. For time being, we can simply say it is simply weighted linear sum. And oftentimes you will see that there is this symbol sigma. And like I said, if your function is very simple, like linear weighted, there's only so much you can represent. But oftentimes what people will do is first you do the linear weighted sum, and then the sigma could be something more that takes in this this sum value. It can be identity, so it's a simple linear network, but it could be something more complicated. So this is a more formal representation of what we have seen. And again, the sigma could be anything, and the sigma is what is called as activation function. So it is almost always assumed that before you apply this activation function, you have done this linear weighted sum. And then on top of that, you'll apply this activation. And if an activation function could be an identity, or it could be something more complicated. Okay, and like I said, this is called as the bias. Now, the reason we were trying to reference linear algebra last time is because you can see here, X is a vector, right? Because you have X that goes from 1 to n. And if you remember last time, we said all these capital letters are your vectors. And then your weights is your another set of vector, right? So in this case, the way we are trying to do a dot product. So what we'll do is a transpose of X. So basically represent X as a row or a column, and W as the other one. And then if you do a vector product, you can now very quickly, and if you have a NumPy, you can simply use NP dot, and then you can compute this and get this value. That's why linear algebra is very important, because if you have to actually write a loop to do this, and remember we are trying here, it's only like few values, but in reality, this could be hundreds of millions. So you don't want to be writing a loop that sequentially does this, because computing this should be done in parallel. And if you use NumPy and if you use NP dot, it will automatically compute this in a very parallel way, and it can do over very, very large vectors. Okay, now this whole idea is is what's called as perceptron. Now, like you saw, obvious idea is to think of multiple layers, right? That is, input of one is output of one is fed as input to the other one, and then its output is fed to the other one, and then so on and so on. And whenever you have multiple layers like that, it's called as multi-layer perceptron. And how many layers, that totally depends on you, totally depends on the application. But as you add more and more layers, you increase the complexity of perceptron, or complexity of the neural network, and that complexity determines how well it can do the task. But of course, there's a downside, and like you guys must have studied in other machine learning classes, there is a trade-off. When you add more free parameters, you need more input, more in examples to train them, more examples to learn. Otherwise, you have this problem of overfitting, right? And therefore, you have to be careful when you add more and more layers, because each of these arrows here represent a free variable, and then the number of examples that you would need to train this increases significantly. So there is a downside of adding more neurons or more layers. So when someone says multi-layer perceptron or MLP, this is what they're referring to. And it is, go ahead.
As we're looking at these arrows, are we thinking of each one of these arrows as a unique feature? So there's 3 features, or are we thinking of it as 3 samples of the same feature?
Yeah, so each of the arrow is a feature on its own.
I'm talking about the initial inputs, right? All the way on the left, you have 3 inputs coming in. Are those 3 input features or 3 input samples of the same feature?
Input 3 features. So these are
okay. So each neuron gets its own. Exactly. Each feature gets its own neuron.
Exactly. So if you're trying to predict house prices, there's one arrow could be number of bedrooms, one arrow could be the square footage, one arrow could be location. And each of your example will have all these features represented. And this is one of the other limitations of perceptron, and we'll study that in detail later on, is if, let's say, for example, in this case, we had M different features, right? So all of your examples needs to have all these M inputs. Of course, you can assume maybe if it's missing, you can assume it to be 0, but you have to provide this fixed shape input, and that is where it is limitation, because often, say if I am trying to learn this on videos, right, and let's say each of this is a frame. Now, I could have a video of different length, right? Or if it is my text could have, and let's say each of this feature is a word, I could have different number of words, right? And similarly, if I have images, and if each of the arrow is a pixel, I could have different number of pixels, right? But this kind of a network assumes you always have the same fixed input size. And this was like one of the big limitations. And that's why you will see most of the toy data sets that you will play with. Also, you will later on play with MNIST and CIFAR. They all have, all the images in MNIST and CIFAR have the fixed shape. Why? Because they were designed to be played with, or designed to be worked with this kind of MLP, and therefore you need to have exactly same inputs for all your examples. Does that help? Okay.
Yeah.
Yeah. So, and now, this is where, like we basically take a leap, and we now, when you have multiple hidden layers, this is where people start calling it deep neural networks. And, for all intents and purposes, this is your deep neural network. When people say, oh, deep nets, this is what they mean. Although in practice these days, we don't use this kind of MLP, we use deep convolutional neural networks. But even deep MLPs are widely used. I work at a drug discovery company, and I use this kind of a network every day. So this is what is when people say deep nets, that is multiple layers of perceptron, and typically the number of neurons in each layer is also in the order of 500 or 1,000. And in this case, you can see here there is more neurons towards at the 3rd layer. Sometimes you have more on the 1st layer. Those things are arbitrary. They really depend on the task, and that is why one of the criticism of neural network is like a priori doesn't tell you how to build this, right? There's no intuition, there's no proper math or logic behind, oh, should I have more neurons in the 1st layer or in the last layer? Answer is depends on the task. So you have the data set, you try them, and this is where ideas are about tuning your neural network comes. That is, you start with a general idea, and then you tune the number of layers, number of neurons, depending on the task, and whatever set gives you the best result, you stay with that. And that is why it is very easy to get fooled by results, because you have so many parameters to tune that in a data set it might look really good, but then when you try the same thing on a different data set, it may not work. And this is where ideas about generalization comes in. That is, if your deep networks can generalize to other data set, then your technique or your solution is called a generalizable. Whereas if each time you have to tune them for the data set, your solution is not generalizable. And the goal should always be to build things that you don't have to keep tuning, because tuning is very expensive, both in terms of time and in terms of, in terms of being fooled by the local business. Okay, now, here we saw input, output, and here you can see, it looks like number of output is also similar to input. So there's a unique kind of a neural network called as autoencoders, right? Here the idea is the number of input is same as the number of output, right? But in the middle, the number of neurons is a lot less than the number of inputs. So far in the previous examples where I showed you, we kind of assume that there are fewer inputs and there are more neurons in the middle. But what happens if, let's say, you have 10 input neurons or 10 input features, but then in the middle you only have 2 neurons, and then again you go back to 10 output, and now you assume whatever is the output is same as the input. That is, if my input are all these features, my output are also the same features. Then you may say, what is the point of this? I already have these input features. Why should I be trying to make a neural network that basically learn? For example, if you go back to this table, basically what I'm saying is, if there's out1 and out2, out1 should match x1 and out2 should represent x2. In that case, why not simply connect x1 to out1, x2 to out2, and you're done. But here the trick is, in the middle you have much smaller number of neurons. So if you think each of this as dimensions of your signal, does a neuron layer K have to always connect to all? That's a very good question, Sanjay. For what we are studying right now, these are called as perceptrons, or also called as dense layers. If you see the Keras, this is what is called as dense. Yes, all the neurons are connected to all the inputs. So these connections are really dense. And you will see, I think maybe not next week, next week, when we study convolutional networks, you'll realize that you don't have to necessarily have this kind of dense connections, especially some features need not be provided to all the neurons. And that is where we'll try to make these connections sparse, and that gives rise to deep convolutional neural networks. So, but for now, for these kind of purposes, when we say dense layers, yes, all the inputs are connected to all the outputs. So in this case, what is happening when you do this, intermediate dimension, which is much smaller than the input? So say, I'm trying to predict house prices, right? And let's say I have, this 10 different features. All these realtors have told me, oh, this feature is important, that feature is important. And then now if I'm able to take all those features and train this encoder so that I'm able to reproduce all these features again, but in the middle, I only have 2 neurons. Essentially, I have done feature reduction, right? Or the dimension reduction of the features. And again, if you have taken machine learning courses, you might be familiar with ideas about PCA or SVD or QR decomposition, right? Or Cholesky decomposition. These are all ideas where can we represent higher dimensional information with a fewer number of dimensions, with fewer number of bits. Or in other words, you can think of this as data compression. I have basically compressed all the features into much smaller, so that now these 2 numbers represent or at least captures the same information as all the input. Now, question is, will it be exactly the same? We'll see. Probably not, because these kind of networks are not going to learn perfectly, right? But are they going to be close enough that you don't need all those features? Possibly. And this is where for a long time, autoencoders was only of theoretical interest. Like people studied it, but it had no practical purpose. But recently, there are a lot of these generative models. And again, if you don't know what are generative models, these are these models that are the synthesized faces right here. Let me quickly show you one website. This person does not exist.com. So if you go to this website, this person does not exist.com, and if you keep refreshing this, you'll get this faces. But remember, these are not some humans faces. This is not from some photo, some photo databases. So this is completely arbitrary, hallucinated by models. So in that these are slightly more complex than this, but the idea was very similar. We take these images and we try to reproduce them, and once we have built these autoencoders that can take a person's face and be able to reproduce them, we can then play with these intermediate values to slightly change them, and then you get this person that, like right now, if I were to do Google search, this person actually doesn't exist, but you can see how realistic this is. Now, the thing is, it was a good, it was a nice, cute thing, but now people have started using these kind of things to have these fake profiles where, they make this fake personality, they steal someone's social security number, have this face, and, it looks believable. If you were to tell me, hey, this is somebody and this person's name is Mr. XY, I'm like, yeah, I can believe that, right? People, those who don't have understanding of AI, they might totally think this is a real person. And that is why recently autoencoders or these kind of generative models have become really useful, because you can generate these really high quality examples that otherwise would not exist. Now there is, so again, this is the idea, right? That is, you take your input image, and now you have this intermediate layer. Now this intermediate is often called as bottleneck layer. Why? Because you can see, it's like the neck of a bottle, where if bottleneck layer is lower dimension than this, whatever you have learned here is able to capture the the semantics or the latent space. So if I were to only train this on cat images, these would would learn how many eyes typically a cat has, typically how long are the whiskers, what are the textures. Now this is where we start to get into kind of like a controversial territory of deep networks, where it's impossible to prove that these latent vectors are learning these useful, meaningful semantic representations. But people have experimentally shown that yes, now if I take this and I can tell you that this really is learning the eye color, because after training this, if I change these values arbitrarily, the eye color of this cat starts to change, and therefore it's a proxy proof that yes, this neuron is learning about the eye color, and this neuron is learning about the whiskers. But again, theoretically, it is impossible to prove that is what is happening, other than just by showing these examples. And and again, the reconstruct data may not always be perfect. Right? In fact, it will not be perfect, but for all practical purposes, it will be close enough that it is useful and useful and meaningful. But you have to remember that the bottleneck layer has to be smaller than the input, because ultimately what you're saying is, I have information that requires 20 numbers to represent, but then you are able to represent it with, like, let's say 4 numbers. It means what? It means the other 16 numbers weren't as meaningful. That is, there was a lot of noise, and by doing this, we are able to filter through the noise, and we're able to improve the signal to noise ratio, SNR. So this is why this is also called as like denoising other stuff. Now this is where I will show you what is a denoising, but this is where the idea of using autoencoders you will see there are really nice libraries online where you can upload your image, which has some noise, it has some rain, it has snow, and these networks are able to remove the snow or remove the noise. Or we can even, Google has this very nice feature on Google Pixel phone where you can remove the people in the background. Or if you are taking a photo of animal in a cage, you can remove the barbed wires or the cage. So how it is able to do? Because by training something like this, you are able to disentangle. And remember, these are the words that are very important, because like if you try to read books, these are the phrases they will use. Disentangle. Disentangle means we are able to take data like this, and we are able to remove what is going to be more common with other examples of similar data set, versus things that are only specific to this particular example. So rain, because those models are trained so much on rain data and without rain data, that they are able to disentangle what part of this image represents rain. And by able to disentangle that, now I can just remove the, so say this one of these neuron is rain. Now I'll just change all the output values of this neuron to be 0. So there will be no more rain in the output. And again, I'm just trying to give you a very simplistic explanation. In reality, instead of using dense layer like this, you'll be using convolutions, and then you'll be using deconvolutions, which we'll study in week 4. But for now, this is still the setup. And we will play with a Colab notebook where I will show you how this works, and on a much smaller data set. But whatever we study right now, these are the foundations of using some of deploying these complicated models. Any questions so far? Okay, no. So now let's so again, now these are the same things which I said to you, but again, points in case you want to remember yourself. Like I said, these are used for generative models, where you can make things that doesn't exist in real world, or you can disentangle information. You can I don't know if you have seen those where it's these apps which can take a person and make them look like old, or make them look like young, or change the hair color, hairstyle. To do all of those things, you need to be able to disentangle these features from the data, and therefore you need these kind of autoencoder type models. And like I said, the other purpose is to reduce the dimensionality of your data. Say your data is so big that you cannot store all of this. You train a model like this and only store the encoded data. And now all you have to store is this, and whenever you need the input, you just only do this part of the model, and therefore you have saved a lot of space. Although practically space is such a trivial problem that people don't do this just to save their space. And the other one is, sorry, go ahead.
Could you go back one screen? Yep. Or sorry, to where you have the reduction. Yeah. So for the eye color example, would the eye color be one of them the outputs that we're seeing on the right?
You mean here? Yes, no. So in this case, I'm just showing you that the same data is, here the goal is to represent the same data as it is. So this is the training part of autoencode. That is, you take in an image and you try to learn this, and you hope the same data represents. But if you try to do that, you'll find that oftentimes the data is not perfectly represented. There is going to be some noise that the model adds. That is why I'm saying that any kind of autoencoder will not be a perfect representation, but oftentimes the representation is close enough that just learning this imperfect representation of data is able to disentangle information. So here, if you have learned this, and now if you want to change the color of the eye, you start playing with all these input neural, all these bottleneck layers, and then a priori we don't know which neuron encodes eyes, but in practice people have found that each of these neurons will encode something like this, something we call it, we call it semantic features. So
okay.
Yeah, but then there's no guarantee that one of these neurons will be eye color and one of them will be whisker lens. But in practice, people have found just by coincidence that it happens. So here, I'm not trying to show you different eye color. I'm just trying to show you that if you try to train like this, your data is not going to be perfect representation of your input. But even if it is not perfect, it is able to learn something about the data.
Gotcha. Okay, thank you.
Okay. And the other thing for which these things are really used a lot is to detect outliers, right? Because if you have trained this on a lot of cats, and then when you try to feed in a dog, these intermediate values will look very, very different. That is, here, is there a way I can annotate? I can annotate, right? Let me see if I can annotate. So let's say, these two features, oops, I thought I could annotate. Okay, I can annotate now, I think so. So let's say this is N1, neuron 1. Let's say this is neuron 2. And I'm just making some. Now let's say the values are like this for N1. and the values are within this range for N2, and this is for all my cat images, right? Now suddenly I get a new, now I pass in a new image, I don't know what image it is, and I get a value that is somewhere here, right, for N1, and I get a value that is somewhere here for N2, right? And now you can see, wow, this value is really far from the distribution, right? Similarly, this value is really far from the distribution. It means whatever we are providing input to this model, that value, that thing doesn't look anything like the images that was used to train this autoencoder, right? Because this distance is so big, like probably you can use normal distribution to find what is the likelihood of seeing a value that is so far. Probably say it is 6 sigma, right? That it is 0.0003% chance that by chance you would get a value so far. It means what we are seeing is highly improbable. It means this thing doesn't look anything like all the data you have trained. And this is what is used to, a friend of mine, he works at a company where they do fraud detection. So whenever you use your credit card, because, back in the day, the fraudulent charges were hard coded. They were like, okay, this person lives in Massachusetts, so whenever there is a transaction in Florida, let's flag it as fraud. But the problem is, if I like to travel to Florida every time I go, and then the transaction is declined because like, hey, you're a Massachusetts guy, you have a Florida thing. So now they don't use this kind of hard rules. They use, this kind of autoencoders where, they see all the transactions that people have done, and then the features could be everything. Features could be your income, how many people in your family and everything. But based on all of that, suddenly if there is there's a transaction that looks so far away, and remember, this is not going to be only 2, there's going to be like 20 others, 20 dimension, and out of 20 dimension, if let's say 18 of the dimension, this value is away from the distribution, then you can say, what, given all of the things that we have seen, this looks out like an outlier. In this way, now we are not able to explain exactly like why is this an outlier, but because network has seen so many examples, it is able to tell that this is really far off, and now you can flag those, and now you can reduce the number of false positives, right? Because you don't want people to get bothered every time they do a transaction that is slightly different than what they have been doing. And so therefore there is a real world use case of using autoencoders to detect fraud. Okay, let me go back. How do I? Okay, so this is an example. This is our use. Now that we have seen perceptron and other stuff, obvious question is if it is 2 or 3 things like this, you can manually figure out the weights one by one, right? But if you really had a big network like that cat example, you can't like sit down and try to compute all the weight values, right? So how are you going to learn these weights, right? And it turns out the algorithm for learning perceptron is the simplest thing you will learn in this course so far, right? Because all the other algorithms we learn will be a lot more complex than this, right? So it really, let's make sure that we understand this algorithm, and I really hope you will, this is not about assignment, but if you really want to, I would say only way to test the algorithm is try to write it down in, try to code this in Python and see you are able to train a perceptron, right? So the algorithm is very simple. Of all your data points, so when I say data points, I mean all the X, right? So I'm not talking about all the different features of X, right? So I'm not talking about this. So I have one cat image. So this one cat has 10 features. So X1 to X10 represents one big X, right? So take all your examples at a time. That is one example at a time, whether it's 10 features or 20 features, whatever it is. And now use that example, do the forward pass. And when I say forward pass, do the computation, do the activation, do the threshold, and see, if the value is above threshold or not, right? Or on the sense, is your prediction correct or not? If your prediction is correct, do nothing, just go pick another value. That is another input. But if your prediction is wrong, right? And now this is the meat of the algorithm. If the output is 0, but the true label is 1, that is, it should be on, but you predicted off, then simply add the input to the weights. Right? So you can see here. So then you start your weights with now the question is, how do you start with the weights? This is the key. Now, a lot of people will do this mistake, and I'm saving you a lot of headache right now by telling you that if you try to implement this is the place where you'll do the mistake. Because if you initialize all the W to be 0, you get into this problem of symmetry. That is, all your weights are exactly the same, and all your weights are getting the same input. So basically, there is no difference between W1 and W2. So they all would rather want to move, or they would not want to move. So you want to break that symmetry by initializing all your weights separately. And the only way to do that is to initialize them randomly. Now, technically people try to just sample a Gaussian and then just add the values. You can try with any probability distribution. It will not matter as far as perceptron goes. But try to keep the weight values small, because if they are too big, then you'll have to train for too long for it to converge. But start with small values, but make sure all your weights are random. No two weights should be same. But of course, don't go out of your way to make them not be the same. Then that is again not really random, right? Now, initialize your weights to be random. And again, if your output is wrong, the logic is very simple. Add the input to the output. Now, this seems, and then if let's say you predicted 1, but the true label is 0, then basically subtract. That's all we have to do. This technically is only 2 lines. In Python, the whole thing should be 4 or 5 lines. And now you keep doing this, that is, take your data at a time, one at a time. And the question is, when should I stop? Like, should we just go through all the data once? In reality, it is possible that you might have to go through your data multiple times. And this is where in deep learning, you'll hear these people talk about epochs of training. An epoch is going through all your data once. And it is very common, in deep neural networks to go through data 100 times. But, for these small examples, probably you won't have to do 100 times. But you just keep adding, and eventually you will not move at all. You will be able to get, get to a place where it no longer changes. And it doesn't mean that all your answers will be correct, but this line will not move. It's almost like training your k-means kind of thing, where it's guaranteed to converge. And if you are not convinced it converges, because it seems too good to be true, here is a link to a proof. Easy to go through the proof, go through the step by step. For lack of time, I'll not go through this, but if you have questions on the proof, I'm happy to discuss with you during the office hours. And then if you also want the code example is here, the example, but I would encourage you to try to write on your own first. And if not, then take a hint from this and then use this as a reference to be able to fix your own perceptron code. Because of course, later on, whatever we will study in this course, for most of the time you will be using Keras, and Keras already has built-in functions to do most of the complicated stuff. But this will be one time when you will be, you could, where you can actually write something from scratch on your own without using any external libraries. And it's a different, I would encourage you to take advantage of that and do it. Because later on, things you don't want to write on your own, because there are too many places where things could go wrong. And you don't want to, reinvent the wheel. But at least for these fundamental stuff, it's a good idea. Go ahead.
I have a quick question about this. So it looks like in this example, it's pretty rudimentary, and it looks like it would be essentially one neuron, right? It's either red or it's blue or whatever it might be. But in practice, as we're coding this, would it be tuning the weight of every neuron in the layer for each iteration, or is it tuning the weight of, a single input in each iteration, right? Or is it isolating the weighting variables per layer, or is it doing it all at once and tuning a layer at a time?
Yeah, so that's a good question. In this GIF here, I don't know if you guys are GIF camp or GIF camp, but in this GIF, each dot is an input example. It is not the weights, right? These are not the weights. So the weights aren't shown here, right? But each of the dot is an input example. And when I say input example, that it could be multiple numbers, because each input example has multiple features, right? That's why, if you remember from on our first lecture, we said whenever you have this symbols, they represent vectors. So here X represents a vector, W represents a vector. So you could have 10 neurons. All your 10 neurons will change for each.
Okay, so the answer is that yes, each neuron in the layer changes simultaneously for each iteration. Yes. Yeah. Okay. Thank you.
Okay. Yeah. Okay. Now, so this is what I will give an example right now. If you see from this, it's clear that the perceptrons learn this linear boundary, right? Again, as long as the activation is simply weighted linear, and then you have a simple threshold, it is always learning a simple line, right? The line is whether it is depending on the value of threshold, you can try to work it out. It's almost like y equals mx plus b, where b is your threshold, right, and m is your w, right? Basically, this is wx plus b line, right? So, but XOR is like this, right? Because if you have x, this is x1, this is x2. When both of this is one, you have blues here and you have reds. As you can see here, no line can help you separate this in such a way where all the blues are on the one side and all the reds on the other side. And again, if you're not able to see that, sit with the slide for a minute and you'll be able to see that there's no way you'll be able to draw one line that can put all the red on one side and blue on the other side. That's why, or in other words, XOR is not linearly separable, whereas perceptrons can only draw linear boundaries. So by definition, this should not be possible. But again, this only implies all these conditions that you're only using weighted linear, and then your threshold is simply one-sided, and you have one layer. But whenever any of these things breaks, you can definitely do this. That is when you are not doing a simple line, you're doing some other function. This is where, I don't know if you guys have learned SVM, where in SVM, instead of using linear kernels, if you use nonlinear kernels, right, then you can do nonlinear boundaries. It's the same problem here. So these are some of the limitations. Okay, now let's come back to, so because of this, it seems obvious that the activation function should be more than simply doing, weighted linear of this. And again, bias is just your threshold. Now this G, this is where the real magic comes in. And for a long time in deep learning, or the neural network didn't advance much because people didn't have idea about G. And, once people started exploring other functions of G, they quickly realized that the whole system is a lot more powerful than what we gave credit to. And oftentimes you will hear, things like, oh, hyperbolic tan or max. And this is where I think one of you said, hey, what if you use max? And you'll be surprised, max is like the most common activation function used. It is technically known as ReLU, R-E-L-U, rectified linear unit, just a fancy name for calling max, because, in deep learning, you want to give new name to all the ideas so that you can claim this idea that you invented the idea. But max is simply this idea that, either value is our certain thing, whatever is that, you take that. But here it need not be F0, it could be somewhere else, but this is what a curve looks like. And hyperbolic tan is where, if you want to bound the output to -1 to +1, you will use hyperbolic tan, right? Because sometimes, what if I want the output to be between, like it's like a temperature, like should I, decrease increase the room temperature, decrease the room temperature, you want to be bounded, because I don't want it to be 100, right? So I want it to be bound to, let's say -20 to +20, whatever it is. If you want bounded outputs, you want to use things like hyperbolic tan, because you can see max is also unbounded. However, if you see the internals of Keras and other stuff, you will see that even max will be bounded at some high value, because it's really bad idea to have unbounded things in deep network. We will learn about that next week. This thing called as gradient explosion or gradient vanishing. But for now, but internal, this will be bounded, but it looks like it is unbounded. Whereas if you really wanted a fixed bounded variable, you will use things like hyperbolic tan, or oftentimes people will use functions like sigmoid, which I'm sure you must have studied in as a logistic regression in your machine learning one, where if you're trying to do a predictive variable between 0 to 1, you will take your input and pass it through a sigmoid function. So now again, let's look at some of the common activation functions, and these are what you will see in most of the applications, most of the tools, and they all have certain reason that they are used, right? So like I said, sigmoid is the most common, and for a long time this was the only activation people used. Why? Because it's very simple, right? Because the values are bounded, right? It only goes so it goes from 0 to 1. Doesn't matter what the input is of x, the output is always between 0 to 1, right? And so this is the equation, and we can see clearly this is not a linear function, so it means it is non-linear. it means it is able to learn more complicated boundaries to separate your data points. The other reason it is widely used in deep learning is, and again, this is something, a prelude to the next week, where you'll realize that you need to be able to differentiate these functions a lot. Why? Because the only way to train really deep neural networks is to be able to do this gradient flow. And again, if you don't worry about it, we have the whole lecture next week about this. But for now, you just have to realize that each function has to be able to differentiate it with respect to x. And the best part about sigmoid is, if let's say sigma x is the function, its differentiation is basically sigma x multiplied by 1 minus sigma x. It means you don't have to do anything fancy, just take that value, right, and multiply it by subtracting with 1, and you got its gradient. It's so easy, right? Because for everything else, like hyperbolic tan, everything is going to be very complicated and a slow process. Here, you don't need to do expensive. That's why it is really used. And plus, things are bounded, so it prevents things from blowing up. This will, but of course, people realize that even computing this was kind of slow, because if you do this in your Jupyter notebook right now, it will take maybe nanoseconds, but we are talking about millions and millions of computation, hundreds and thousands of times over. So you can see how that small time adds up. So that's where max became more widely useful, because computing max is very simple, right? It's almost free computation. Simply, if the value is below a certain threshold, make it 0. One second, let me turn the lights. 1 second for. Can you guys still hear me?
Yes.
Hello, can you hear me?
Yes.
Yes. Can you hear us?
Hello. Okay. Someone said yes. I'm guessing that's for me. Okay. So this is the benefit of sigmoid. Let me check the. Okay, perfect. Now there are other functions, and again, you don't have to like step through every one of them. Of course, identity is when the same input, and you can see this is what perceptron uses. You have this binary step, which would be most ideal, like 0 to 1 thresholding, but you'll see that this kind of things is not differentiable, right? Then you have this logistic step. This is sigmoid. Then you have hyperbolic tan, arctan. Some of them are not as common, and you can see here ReLU is same as your max. And then you have, and then there are more complicated ones will come to us later on, but these are like the ones you will hear in textbooks or in people's blogs. Now, this is ActiveBase, right? Now, ultimately, you have this setup and you have the data, and we know how to, even optimize it. But the main question to ask is, what is that we're trying to optimize, right? But like, how are we trying to train the weights that we know we have succeeded? How do we know that we got to where we are trying to get, right? So obviously we're trying to do classification. You want to reduce the amount of classification error. But just because I want to reduce classification error doesn't mean there is a way to write that down in a programmatic way. So oftentimes you will hear the word called as loss function or the optimization function. So loss function is something that is mathematically possible to write down, and yet is very close to your objective that you want to do. In my, if I'm trying to do classification, my objective is to do the best classification as possible. But there's no way to codify that that idea, right? What does it mean to be best, right? Because I want to be able to write some values such that for each example, I am able to compute what is my error based on where I am versus where I want to be, right? Because if you see this, if you remember this perceptron algorithm, there's no notion, at no point in time I'm telling you how close you are to convergence, right? You don't know, like you don't know if you're improving or not. I just told you that here is a proof. You have to trust me that if you keep training this, you'll do better. But it would be days, and in the middle, you don't know if you're improving or not, because there's no idea of a loss function here. But for most of the time, real world application, you want to know how well you are doing. So you want some kind of a loss function. So function is something that typically we minimize, but it could minimize, maximize, just change the sign. It'll be, it'll be the same thing. But more importantly, it depends on the task I'm trying to do, right? If I'm trying to predict house prices, it's some kind of a regression task. So the more loss function will be more like how close I was. If I'm going to do classification, I will count like how many errors I did. If I'm trying to generate new images, I want to say how realistic it is. Now, you see, the idea of a realism is something, it's hard to codify. Like if I had to ask, okay, write me a math equation that tells me if this image is realistic or not, it's impossible to do because, it's in our head, what is real, what is not. But people have figured out proxies. That is something that is close enough that will do the same thing. And of course, the other reasons to consider while picking loss function is what kind of output do I want? Do I want completely unbounded output? Do I want discrete finding? If I'm trying to predict, a number of, the star movie will get. I know there can only be 1, 2, 3, 4, or 5 stars, right? Therefore, is it discrete? Is it bounded? These are the things, and I want to see how sensitive it is to the outliers. And again, these are some of the things I'm sure you must have studied a little bit in your machine learning course, but for deep learning purposes, these are even more these are even critical because if you pick a wrong loss function, you would get a complete garbage. And oftentimes, most of the time, these networks will be like really garbage or be really good. There's nothing in between. And that is why it's important to know what you want from a loss function and pick accordingly. And again, we will go into specific loss functions more in coming weeks, but just wanted to give an idea on like what are some of the basic loss functions, because these are going to be our building blocks. Now, and again, I'm going to assume that you guys know what is L1 norm, L2 norm, the Euclidean distance, and other stuff. But again, just in case you need a refresher, L1 norm is basically, some of the absolute values, right? Here, F represents, the output of the perceptron, and Y represents the true values, right? So you subtract this and you take absolute, that is whether you are up or low from the true value, the error is equally penalized. That is the true, it's like almost like, I don't know if there's some game show, right? We're supposed to predict the price. But in that game show, if you are under, you are still good. But even if you go higher by 1 cent, that is penalized differently. You are completely out of the game, right? But so those are asymmetrical. In this case, it is symmetrical. Whether you do $2 less or $2 more, the penalty or the error is the same. But oftentimes you can see these kind of things are going to be very, very sensitive to outliers. Therefore, you want something that is less sensitive to outliers. So you use L2 norm or the Euclidean distance. And these things are good if the value you're trying to predict is more continuous. But if I have classes, that is cat versus dog, then I can't do that. And for that, we'll use something like a cross entropy, right? That is, you take the log of the prediction and then you multiply by the true value, which in this case will always be either 1 or 0, and then you get this. Now, question is, how do I get more discrete values out of this? So you have to take your input of this perceptron. Like for example, this might just be continuous value. You have to make this into a probability distribution before you use cross entropy. And again, this is where I'm hoping you guys have seen this before. If not, feel free to stop at office hours, and I'm happy to walk you through what is cross entropy and how and why we use this. But you need to be able to change this output of a perceptron into a probability distribution. That is something that goes between 0 to 1. That is where people use functions like this, right? This is your softmax. That is, you take the exponential of the values, divide by sum of all exponents, and this whole thing is always in the range of 0 to 1 and is considered as a probability distribution. Here's a question from Kyle. For the L2 versus L1 norm, we see squared error all the time in statistics. Why is it so much more common than L1, say, or say an L4 norm? That's a very good question, because the gradient, because especially for these purposes, the gradient is much smooth for L2, right? That is, in this case, the gradient would be 2 multiplied by this. So therefore, as the values get smaller and smaller, the gradients will also get small. But in this case, the gradient will remain the same, and therefore it quickly converges to 0. So therefore, if you really want sparse, that is, if you want a lot of the weights to be 0, you would use L1 norm. But most of the time, we just want to control the values, but not necessarily want to make it sparse. So, there is more nuance to that, but L2 is often used if you want. Now, question is, why not use L3 or L4? You could, they're same thing. In fact, there is a sometime later we will be using L infinity norm. right? Because so L3 norm is now in this, in L2, I want to say, okay, all my values has to, you know, I don't want to penalize big outliers too much, all right? But I want to focus on values that are close enough to the true target. But what if, you know, say I'm trying to predict a model where, you know, will this person survive if this, you know, if they cross this lake, right? Now, in that case, I don't, you know, I don't care whether they're, you know, some parts of the lake, the person is able to swim easily or not. I care if there is some part of the lake where he will, you know, drown. In that case, I'll use a L infinity norm where one part, like one error, could completely destroy the whole thing. In those cases, it's not about all these small errors. It's about one big error that will be bad. So there are cases where you'll use something in between, but typically L2 has a nice smooth gradients, and that is why we use, and plus it is also more intuitive. Yeah, but you know, you could use L4 in place of L2, and probably the application would work as it is. And again, cross entropy is something very useful if you're trying to do classification, but you have to remember to convert the output of perceptron into a logic. They are also called as, say, into probability. So the value before you do the probability is called as logits. And this is the word that is being used. That is the final output of a perceptron is called as logits. And then when you do this softmax thing, it's called as probits or probabilities. And then, you know, you use that and then do a cross entropy. Okay, now the other thing that you will hear a lot, and you know, we will study in more detailed regularization, but just wanted to give you a peek. It's very common to use regularizations in deep network because, like I said, the number of free parameters in deep nets is always a lot higher than the number of free parameters in, you know, other standard classical machine learning tools. So therefore, it's very, very possible that you'll overfit. And when I say overfit, it just means that you have so many free parameters that they'll just memorize the training set. So it has a very low error, low loss on the training, but very high loss in the validation. So in order to prevent that, it is very common to say, okay, if this is what my loss function looks like, that is there's some error, L1 or L2, I will add some kind of penalty that has nothing to do with my error, that has nothing to do with the task at hand, that is just to make the training harder, or it is just to make it slower to achieve that training. And so in this case, if you simply do a L1 regularization, you're trying to minimize the L1 norm of the weights. You can see there's no inputs here, right? That this has nothing to do with the examples you provide. You're simply saying that given all the weights, I want to choose a network that has slightly smaller L1 norm or slightly smaller L2 norm. And again, in practice, you'll use L1 norm if you want few of the weights to be 0. You will use L2 norm if you want them to be small. But in reality, if you're trying to do regulation, it doesn't matter much. But if you're not sure, stick with L2 norm because it is easier to train. And you know, I've been using this word easy a lot, but you'll definitely see from the next week onwards when you start training your own neural network that oftentimes you have all the right ingredients, but things doesn't seem to work as you would expect. Why? Because there are a lot of other unsaid things that make some of the training harder or easier, and knowing these things can definitely be critical in being able to get the right results, right? Because, you know, unlike your standard software where you can write a test, okay, right? You know, you have a function and you write a test and for that function, and either you have the right implementation or you have the wrong implementation. And as long as you have the test, you'll be able to catch it. But in machine learning, you can have the right algorithm, right? That is, it passes all the tests, and yet you can get a poor result because optimization is not, you know, the optimization is subpar. So right algorithm plus you need the right optimization. And that is why, you know, in machine learning, there's, you know, a lot of people complain about it being kind of an art because there is a lot of these nuances that you have to play with in order to get good results. Okay. Now, you know, again, this is we'll study in more detail, but because I gave you, because I told you about autoencoders for images will actually use convolutional neural networks. And again, none of these words should make sense to you, and I will go in like excruciating detail in the future weeks, but just to give an idea that, you know, if you hear autoencoders and if they're using images, probably it is using convolution and not you know, your NLP. Right? Now, denoising autoencoders is something that is very interesting because it takes an image, right, it artificially, you add a noise to the image, and then you tell the network to reproduce the image, not the noisy one, right? Because you're giving the noisy input, but you're asking the network to reproduce the non-noisy version. And you might say, what is the purpose of this? Purpose is somehow by doing this, model learns to remove the noise so that tomorrow when you actually do get a noisy image and when you pass it, the model quickly is able to remove the noise. And for a long time, this was the kind of thing that was very common to use for with images and other stuff. And therefore, it's a way, because if you're trying to play around with autoencoders, good idea to play with denoising autoencoder, because now it's easy to evaluate how well you did, right? Because now you see what has been generated and compare that with the clean image versus the noisy image. If it is closer to cleaner image, you are improving, right? You are in better shape. But if it is closer to the noisier one, you haven't been able to remove the noise. So this is a much easier or more, more permissive way to train autoencoders, which also have some real purpose, right? Now, again, this is just sneak peek, but just to give you like a high level of how to do how to do this in Keras. Here, of course, first import Keras. Now, again, if you're using TensorFlow, because TensorFlow already has a Keras inside it, so you can use from TensorFlow import Keras, and that also works. And like I said, all these things are called layers. So you'll do from Keras import layers, and now encoding dimension. Right, this is the number of dimensions. How many neurons do you want? And now here you can say input image. Now the shape is the number of pixels in your image. Here it is 784 because MNIST has 784 pixels. And again, MNIST is just a popular data set that you can play with if you're trying to do this. So you'll add one hidden layer. So it's called layer.dense, and you will say how many how many neurons you want, which we said 32. And again, activation is the function, right? Which you can do ReLU, you can do sigmoid, whatever you want. And this is the input. Now this is the hidden layer. And now you do another. Sorry, this is a bottleneck layer, right? This is a 32 units. Input was 78. Now you want the output to be 784. You want output to be also 784, right? This is what we studied an autoencoder looks like. Now you do decoded, again, layers are dense. The size should be, in fact, it is best to write a variable here called as input dimension, and then use the same variable here and here, so that tomorrow when the input dimension changes, it will change at both the place. And again, you can do activation here. In this case, it is sigmoid, because in the for images, the values are always between 0 to 255 or 0 to 1 normalized. So by doing sigmoid, you'll get a value between 0 to 1. Now you can do, now you have to encapsulate it in a Keras function called as Keras.model. And once you have done this, autoencoder is a object of type model, and you give what the input is and what the output is. And now you can, sorry, so this is the autoencoder part. This is, if you want, you can, now this slide is not necessary, but if you only wanted to see the encoder part separately, that is, this, if you only want to be able to get the output of this, you can try to write this like this. Here you can see here, I'm removing the encoded, right? Encoded is this one. This the autoencoder is the full model, full architecture, but encoder is only half of it, just in case you want to play around with the intermediate values, to see whether it's learning some latent representation or not. And now you provide the encoded input, do Keras.input, give this shape. Decoded layer is, again, this is only to extract layers. You don't need all of this. In order to compile, you can see you only need autoencoder. So none of this is important. You can just do autoencoder and then optimize it. Now we'll study a lot about optimizing in the future weeks, but for now, just use this as a function that will automatically tune the weights. And again, don't train this with your perceptron loss. So perceptron algorithm, it will take forever, but you can use this optimizer.atom loss binary. And now if you want, there is a much better example here. And again, this is a notebook. Everything is here. Try to play with it. You can see the denoising where the noisy version was given and the model is able to reproduce the unnoisy one, or you can do a normal autoencoder where an image is given and this is a reconstructed, right? So like I said, it's not always going to be perfect. So some of the details will be missing. Like for example, if you have text, the model doesn't have enough capacity to be able to reproduce this text. So all the text will get blurred like this. If you have a lot of details like texture, it will get blurred. but the major parts of the image, like the big things, they will be represented. So if you want, so the first thing I would say is look at this code, simply go ahead, connect, and then run all of it and see the examples if it comes, and then go through the code one by one. But after you have done it, try to see if you can do it on your own without looking at this. And again, this is not an assignment, but this is only for you to get familiar with autoencoders. Or you can just run it and then start playing with the intermediate values, changing the number of dimensions, seeing it improve the result. Try to plot the loss function to see how what is the optimal bottleneck size that will give you the best results. And in that way, you will also get a sense of this idea of curse of dimensionality. That is, when you have more and more dimensions, the problem gets harder and harder. So and this is this is a fashion MNIST. If you want, there is also a true MNIST example also. Like for example, here you can do MNIST also, and it has the same sizes, same shape, but the images are just digits. So here, let me see if it will work. If I simply do this, and if I replace this with MNIST, it should also work, I hope. I didn't run this, I need to run this, and see, now I have ran this. So now if I come with this and if I run, I should be able to see the examples. Yes, where is the, how do I print example? Okay, there's no code to actually plot the examples, but you can, if you try to plot these 2028 using Matplotlib, you should be able to see these examples. So I know we're a little over time, but I will stay for another 5-10 minutes, however you guys want. If you have any questions, you can ask me now, or if you guys want. So for office hours, I thought, I don't know if you should have a fixed time, or we should do it by appointment, where we have the Slack channel. You guys can message me when it's best, and then we can figure out a time based on your own needs. So I'm happy to do either stuff, but I will stay another 5-10 minutes today if you have any questions.
Thank you.
No one has any questions? Tim, you have any questions? Okay, so if you don't have any questions, please look at the modules, try to play with this. The only way to learn this is to get yourself familiarized with Keras and get yourself familiarized to training these things. Okay, I will stop sharing and I will